Hey everyone, thank you for joining today. So I wanted to talk about this paper. I feel like it was kind of interesting topic. I'm kind of curious about generative AI and um, and I work with Sergey on the causal learning team. So I don't know, I kind of wanted to dig into this paper a little bit and explore. But yeah, so it's called the Causality Variational Autoencoder Network for identifying the potential biomarkers of brain disorders. So, as we know, generative AI is really popular now. It's really cool. It's exciting to see all of the cool stuff that it's doing. So I kind of, I guess, wanted to talk a little bit about generative AI. Like, what is it? How does it work? Kind of. What are potential uses in neuroimaging, causality, modeling, and stuff, and then just kind of dive into the paper. So I guess to start with, so why do we care so much about generative AI? Why would it be cool or interesting? But I think there's, a lot of different reasons, obviously. So one thing that's kind of cool, I think about like generative AI is that there's many right answers. So there's not always a single set correct answer per se when it comes to a lot of these kind of tasks that generative AI does. So like multiple valid outputs could exist for a single prompt. So you can kind of see that here with these images. And then also too, those certain tasks, I think generative AI is just intrinsically good at doing. For example, this is image super resolution. And some of these images were generated using different kind of generative AI models. And not only that, but yeah, we can use generative AI, I think, in a lot of ways in our lab. One way that would be kind of interesting is something like neural manifold learning, or just kind of trying to understand like maybe latent dynamics and brain activity and things like that. Um, so I kind of found this like a survey paper, kind of dissecting some of this stuff, building it up a little bit, kind of giving a little bit of a background. So I think I just kind of am using this to kind of guide this talk. But yeah, if you're kind of interested, I guess, in some of these topics, you could kind of dive into this paper here. But I guess just to kind of start the talk and kick it off is just talking about, principal components. Principal components, as we know, they're basically just like the orthogonal directions of the greatest variance in our data, and we can use those to perform what we know as principal component analysis. And so PCA is, basically a data reduction approach that just seeks to find like the optimal representation of projection of the data onto its principal components. So basically, the goal of this is to preserve as much information as possible in the data, and it projects the data onto the principal components to that. But how is this connected to, I guess, generative AI, deep learning stuff? So we also know about the autoencoder, and an autoencoder is an artificial neural network that learns efficient encodings of data. So basically, autoencoders are like a nonlinear form of PCA. Because they reconstruct the input while being constrained to the L2 loss to encode the input to a lower dimensional space, and then reconstruct the input again. So that's one way we can kind of start thinking about this. And then another kind of concept I think that's driving this kind of research is something called factor analysis. So it's like a generative model that assumes the data that we observe is generated from a set of latent variables. And it assumes a linear relationship between these observed and latent variables. So, so I think this is one way. Another form of kind of like generative modeling for data And then kind of similar to this analogy we had earlier with the BCA and autoencoder, we can kind of think about the variational autoencoder as a form of nonlinear factor analysis. So variational autoencoder is basically like a probabilistic spin on the traditional autoencoder. And it's instead of just mapping the data down to the lower dimensional space, it tries to learn probability distribution from which we could sample latent vectors and use those to reconstruct the input. So now we have a latent space. So I guess we kind of need to get into the background a little bit on the variational autoencoder. How do we go about training something like this? So I think we can start with the assumption of kind of like this factor analysis thing that we talked about, which assumes that the data that we observe is generated from a set of latent variables. So we can just say that X is a random variable representing the observed data, and we can let Z be a random variable, which is kind of representing the set of latent variables. So we basically want to do two things here, which is we want to maximize the likelihood of observing the training data. So that's what this P of X probability distribution represents. And then we also want to model the latent factors given the observed data of X. So basically how this works out is, so you can start thinking about this conditional probability of observing the latent variable given the data X. And you can rewrite this probability distribution using Bayes' rule. But then kind of arises this question of how do we actually evaluate this probability distribution in the bottom of this fraction. So I think most of the time this integral here is intractable basically because of this latent variable Z. It can obviously be like high dimensional, and so this is typically considered like an intractable integral. So then I think how people are kind of working around this with this whole VAE thing is they're using variational inference to estimate this intractable probability distribution. So basically the goal of this is to do three things, which is to find this estimator to match this intractable probability distribution such that it's approximately equal to it. So kind of how this evolves is we can estimate the difference between these two probability distributions using the KL divergence. And then from there, we can just kind of, it kind of can boil down into this term here at the bottom, which is an expression of so it's an expression of the fitness of this estimator as a factor of these two terms. One of these terms is evidence, and the other one is this term called the evidence lower bound. And so this KL divergence term on the left-hand side is not going to be greater, is not going to be less than 0. So since that's the case, we can use this term here, the negative term, as a lower bound to the evidence. So basically what people do from there is they rewrite this last term, which is called the elbow, evidence lower bound. And essentially you can boil this down into two terms that are, pretty interpretable. One is the reconstruction loss of how well our VAE can reconstruct our input data. And the other is just an estimate of a measure of how well the posterior can estimate the prior. So that's kind of the background of the VAE, kind of how people are actually kind of training this is they're using this evidence lower bound. Now, how this paper kind of gets into the causal realm is they use this thing, this kind of concept called structural equation models. And which these structural equation models are basically the problem of determining the causal structure among a set of unmeasured variables. So this basically takes this form here. So these structural equation models, they don't necessarily have to be linear, but this is the general form where basically we're looking at these parents, which is this PA term, and standing for the set of variables judged to be immediate causes of X. And these new variables represent errors or disturbances due to a new form. So this is just kind of a buildup of what they're using in the paper to kind of do their causality analysis. And but in the paper that I'm talking about today, they use linear SEMs. So this is the form of that equation. So here, instead of having this PA term, it's corresponding to these variables on the right-hand side of the equation that have non-zero coefficients. And so basically, this x of I is the dependent variable that we're modeling. X of k is the independent variables that influence each x of I. These alphas are the coefficients representing the strength and direction of the relationships between variables. And the use of I are the error terms, which account for the unobserved influences / noise. And these structural equation models may also be referred to as covariance structure analysis, analysis of moment structures, analysis of linear structural relationships, and as well as causal modeling. So I think pretty much what they're trying to do here is they're looking at latent variables. So what does that particularly mean? So they're kind of like a concept which they're not necessarily directly related or directly observable. So some examples of that might be intelligence or social capital. But however, these latent variables, they are measurable using the observable variables that we have. So for example, we might be able to consider the variance of a questionnaire item as being caused by some kind of a latent variable, which we would like to measure. Or
just in one direction, this sounds a little bit like I was teaching just refresher of the algebra of the class. And I was showing an amount, but there is of a matrix of movie preferences for people. So movies, movie names, and people and their preferences. This is observable. When you do economics matrix factorization, you can see that some of the latent directions there represent genre, horror, and like horror direction, comedy direction, and you see how people structure by that. Also, kind of a hypothetical thing, right? But we know it in each movie. We can look at it and say, but from this data, it is not revealed to us. It's late. So it doesn't have to be something that you cannot measure directly. You can measure it directly too, but it's not directly measurable from the data set that you have at hand.
Mm-hmm.
It can be something that, well, like we have tests for intelligence. We can probably devise tests for social capital.
Yes, yeah, it is kind of I guess mystical, but probably because I'm not explaining well. But so another thing I think that we need to be aware of in this paper is are these terms called exogenous and endogenous variables. So endogenous basically just means dependent variables. These are caused by variables in our system or model. And then we have exogenous, which are just basically independent variables, which are kind of outside of the influence of the model. So yes, so that's what we're going to look at next. But the cool thing about SEM models is you can represent them using these path diagrams. So we have this kind of like an ellipse shape. What that represents is the measured latent variable. So they're, again, like Sergey said, the underlying unobserved constructs that influence the.
So they're not measured.
No, they're not.
Yeah, you said measured.
Oh,
they're latent variables. That's the point. We do not measure them. Observed means measured in this case, right? The second one. Manifest, observed manifest variable is something that we have data from.
Okay, I guess, oh yeah, because I guess we do have these observed variables, but we use those to measure the latent variables, but I guess
To infer.
okay, infer. So yes, and then so we have these observed variables, which are represented as a square, and we have the error variance or disturbance term. I think this is some kind of an error that will be introduced to the model for some reason.
Kind of intrinsic noise of the system.
Mm.
It's I don't know an example, but it's something you follow orders, but sometimes you don't. Why? Not because some other order came. It's just like you have internal free will. Source of noise.
Okay.
Source of randomness from perspective of the person giving you orders. It's just sort of randomness inside of it. But it's a concept more than anything. Like every random variable has influences, but it also has its own generator.
Mm. Okay. Yeah. Okay. And then we also have this kind of double-headed arrow, which is representing covariance. So it's not necessarily implying any kind of a direction between entities. And then we have this regression or directional path, just represented as a single-headed arrow. So this is an example of a path diagram. So so we're basically looking here at measurement models. So 801 here is a latent variable, and it's shown as an ellipse. And so according to this graph, 801 is shown to cause observed variables x1, x2, and x3. So we can also think about eta as being inferred and measured by the observed variables x1, x2, and x3. So at the top of the diagram, we have three error variables, E1, E2, and E3. Those are the errors for each of the equations that 801 is creating.
But imagine that eta x1 arrow x1 is some function. Whatever the value of eta 1 is, we can compute the value of x1. But what we will actually measure is not that direct functional computation. We will measure this number plus the noise that is intrinsic to x1. So that's how this functional relationship turns into probabilistic relationship. Now we have probability of x1 given eta 1 because we do not have exact x1, although we assume it's somewhere there.
So here's another example where we have these two latent variables and 6 observed variables, each of which has an error term. So there's now a curved line with an arrow at each end. So you can see here, eta 1 and eta 2 are the two latent variables that are correlated now. We don't necessarily know the relationship between these two, but they are correlated. So I think in this example, these two are exogenous variables because they're not necessarily influenced by anything within the model. And then we can think about a graph like this, which is where we now kind of introduce this theoretical statement about the direction of the relationship between these two latent variables. So there's no longer this like correlation between them. One of them is causing the other. So you can say that eta 2 is a cause of eta 1. And so because of this, eta 1 is endogenous and eta 2 is exogenous. Yes.
Just to continue, just quickly, I don't know if I'm helping or otherwise. But in this case, eta 2 would itself be disturbance term.
Oh.
But it depends. Like the only thing about eta 2 now is its intrinsic randomness. It's not being influenced by anything, so it has its own PDF probability density function, and then it influences everyone. That probability density of the intrinsic function. Like what does it mean to be cut off from other influences? It's just your own random number generator. It's giving so
Okay. So yes, so getting into the paper, so they kind of base their kind of problem setup based on this SEM theory. So they propose that we have the adjacency matrix A, which is just a weighted graph with M nodes. So for us, these M nodes would be M brain networks. So they're saying, according to SEM theory, the causal relationship between M brain regions can be expressed using this equation here. And so where these terms represent different things. So Y matrix is the Gaussian exogenous factors, I guess like the external noise in the system. X is the fMRI time series data, and D represents the length of time series. So for us, this would be like an ICA time course matrix. So from what I can tell, this matrix M is the coefficients of this SEM model. And this matrix A, again, is this adjacency matrix, which represents the directed influence of the regions on each other. So the goal of this paper is, given the distribution of Y in the samples of X, where X is, particular subjects, ICA time course, and then N is the total number of training samples that we have or subjects in the data set. Their goal is to use the variational autoencoder to reconstruct the sample K, subject to maximizing the evidence lower bound, kind of expressed here using their problem setup. So this is kind of what their encoder architecture is looking like. So basically they take in the time series data X as input to the encoder. And so they have, I think, an MLP that's learning these parameters, MY and log SY. So these just represent the mean and standard deviation of the probability distribution that will be used to sample this matrix M. So once these are learned, they're multiplied by with the matrix M, and then Y is sampled from a Gaussian with mean M and standard deviation S. So then Y is multiplied with the inverse of the matrix M, and from there they solve for the matrix A, which is the adjacency matrix.
So that was a structural connectivity based on what previous model is.
So M, from what I'm understanding, M is like the causal structure that the entries of M represent the coefficients of the structural equation model that they're using to like infer the causality from the fMRI time series. Then they estimate the adjacency matrix A from this matrix M. So using this matrix A, basically the decoder just tries to reconstruct the fMRI time series to subject to that elbow lower bound.
So they just minorize M in order to create the adjacency matrix. Is the adjacency matrix just edges, presence, and absence, or?
So they solve here for this matrix.
It's that it's minus
Minus the mean.
No. M is the like coefficients matrix.
Yeah, but coefficients matrix is already adjacency matrix for a directed in a linear model.
Oh, then well I know.
Well, it's a weighted adjacency matrix in a sense.
Yeah, I don't think that I'm not sure, but I don't think the M matrix is directional necessarily. I know the adjacency matrix is obviously.
No, adjacency matrix doesn't have to be directional as well, but M matrix has to be directional if you write X equals M times X plus noise or Y equals M times X. This is directional. a specific element of Y depends on specific elements of X, and it's not vice versa. It's a, there is a functional connection.
It shows the causal relationship between different frame regions.
Under assumptions of everything, linearity and everything. So what is V? What is the square nodes? Each square node, what is that? A voxel?
Yes, I don't necessarily think it's a voxel. I don't know why they're called V. It's a visible layer. I think that maybe is what the V stands for, but I think they're processing it into regions of interest using an atlas.
I think it is not voxel, it's based on the paper, it's regions based on aerial atlas.
Yes.
But then what are the latent variables? What are the latent regions? So they they don't have any compression of the latents, right?
Okay, so the dimension of Y, I think Y might be the compressed.
Is it the number of regions in the atlas by number of regions in the atlas? What is the dimension of M and A? How many nodes are there?
Yeah, so M dimension, let me see.
Yeah, I don't want to really
No.
talking. Yeah.
I think M is an M by M matrix as well as A. I think A is also an M by M. Yes, A is an M by M.
So usually I think of Autoencoder as the way you showed it as something that would be projecting into another space, but this one is rather doing a transformation, right? M-dimensional vector gets transformed into M squared dimensional matrix.
Yeah.
In the bound, in the middle.
Oh, yeah, well, I think there's not, yeah, so it learns the mu vector, like the mean vector, and then it learns.
Or each element in an M matrix. It's a transition matrix, right?
So it learns what I understand, it learns a vector representing the mean of each dimension, and then it uses those mean values to like diagonalize a multivariate Gaussian that represents the matrix M.
So if you call the vector, then it's M squared element vector because it needs a dimension for each element in M. So it's a matrix.
I think Y is a matrix, X is a matrix, but the M sub Y that is learned by the model is a vector, as well as the S sub Y, which represents the standard deviation values. So both of these are used to construct the multivariate Gaussian, from which M is sampled.
Why is the noise matrix?
Oh, what was the question?
Why is the noise matrix?
The noise matrix. Yeah, why is that there? I think
I thought it is the noise matrix. I can ask a question. Based on the paper, it stated that why is the noise matrix? It will present the independent fluctuations, exogenous factors.
yeah, so I think we need Y somehow to solve for A. But yeah,
It's not yet. Yeah, Najmi is not asking a question. She just read it from the paper.
all right, so no, yeah. Any other questions? So yes, yeah, so what they do, and this is kind of just a brief overview of how this works. But like I said, they take the fMRI time series and they use the AAL atlas to separate it into these regions of interest, where each region has its own time series. And then they provide this as input to the model. And this model tries to reconstruct the fMRI time series as we just described. And so once they train this model using this elbow lower bound, they just throw away the decoder, and then they encode the entire data set to this adjacency matrix representation. And from there, they use the adjacency matrix as input to a classifier, which tries to predict the disease or diagnosis of the subject. And so they did this and compared this to like a few different ways to represent the brain, the causal relationships in the brain. So they did this with two data sets. The data sets that they used were the abide and the ADME data sets. And again, they used the AAL atlas parcellation. So like I just described, they compared this to, I think, like 7 different methods. So they compared with the Pearson correlation-based method, the sparse low rank representation method, Ranger causality method, transfer entropy, linear non-Gaussian acyclical model, temporal lag neural network, and causal recurrent variational autoencoder. So I think this is something kind of similar to what they're doing. I'm not sure, but so this is the results that they're getting. So it looks like each one of these methods were the average was used as the final result, and they did 5 runs of each method, and the best scores are available here. So it looks like their method, which is this CVAE, achieves the best classification performance in all the tasks with accuracies of 75.6, 82.6, and 74.4. So this is kind of indicating that their method is learning some kind of meaningful causal relationships. And so for the Abide data set, there are, I think, 6 different sites, or maybe 5 sites. So they did these tests again on all of the sites. And so they found that their model was performing better than competing methods on most tasks. However, they were having some weird results on the NYU site. They think maybe it's because of some kind of an imbalance of the data on the site. But they're still kind of yielding this higher accuracy on these 4 independent data sites. Accuracy. So another analysis that they did here was so they looked at the feature importance of these adjacency matrices to this classifier, and so they use some kind of like feature ranking algorithm to look at basically which predictions were most influential to the model predictions. And so this is what they were noticing here. So these plots are hard to see, but the ball is representing the strength of the causal relationship. Oh, sorry. The ball is representing the causal relationship, and the arc width represents the connection strength. So they were kind of noticing these biomarkers for these particular groups. And so they noted that it aligned with similar findings in other work. So another thing that they looked at here, so they basically froze their model weights at the middle layer, and then they mapped these activations back to the brain according to the Atlas ROI map or mask. And certain activations had higher values indicating higher importance to their model. So they did this for each group and took the average of these activations, and then they compared all the groups together, plotting the difference in between the groups. So this is what they were finding. So in this plot, closer to red is a more significant group difference. And so for the ADNI data set, they were noticing abnormal regions in particular areas of the brain. And as well, they were just kind of noticing these kind of findings. And so another thing that they looked at was the reconstruction error. So they mapped the entire data set to a latent representation, which is the adjacency matrix A. And then they used the average latent representation for each group to recreate the average reconstruction for each group back into the brain space. So from there, they looked at the difference between the reconstruction error for each group, and they compared them with the differences in healthy controls reconstruction errors. So I think with these areas that have a higher reconstruction error, you can obviously tell there's something different between the groups that they're comparing them to. So that could be an indication of some kind of like an anomaly or something that could be used as a biomarker for a specific group difference. So that is, I think, concluding the presentation today. So in short, they designed this deep causal variational autoencoder to estimate causal effects between brain regions. So they achieved good performance on these tasks that they did with these two public data sets, the ADNI and ABI data sets. Future work, maybe they could see if the results are strengthened at combined time scale. They could try using a noising variational autoencoder to improve the result. And they could explore the learned causal manifold and maybe some kind of intervention tasks to possibly change the outcome of certain results. Yes. Okay. Does anyone have any questions or comments?
Sorry, just go ahead. So what exactly does by data set entail? Because I know adding is a I'm just really curious. Something a little more specific than
Yeah, it's Alzheimer's.
Alzheimer's. Okay, so
Yeah.
do you think this model would work really well on something a little more less controversial than else? I'm curious how that would run different data set.
I'm not sure. So what would be an example of something that would be more controversial in diagnosis? Because I think they're looking here at this early and late mild cognitive impairment, which maybe is a good example of kind of what you're thinking of, but I don't know, what would be
I think early cognitive impairment was hard, late for setting, so that could also, I mean, autism could had different groups, I think, back in the 1990s. I think it changed in 2000 something, was high functioning autism, Asperger's, Rett syndrome, and there's another, and I know that there's been papers published about schizophrenia. It's a similar issue, so I'm just kind of curious. Dementia is can be clinically assessed, but also neurologically examined. So I'm just kind of curious if the models generating those biases, those two, those are my initial thoughts. I think that's the reason mistake, and I'm just kind of curious about that too.
Yeah, I think so. Yeah, I mean, they did. I think they're kind of addressing that by looking at this ADNI data set. But yeah, I mean, the results are there.
Yeah, but I think what Jordan is asking is more like if I had a simulation data with known ground truth, then it would have done more good for us to see where this method stands relative to the other methods they compare. Because at nearby, it's a research question, right? We don't know the ground truth.
Yeah.
And how do they even, how do they, like, what are they even comparing in terms of, they're just comparing predictive errors. They're not comparing the structure that we selected, the graph structure is correct. They're like, this graph structure can be used to predict.
So I think so they do have like a supervised learning task, which is these results here. But then I think this is more of them kind of looking at like unsupervised results. So these are comparing the kind of things that they learned kind of like from causal differences between groups. So we don't, this is just kind of a comparison. So there's not necessarily a label for this. It's kind of just looking at,
No, like if they knew this arrow is present, that arrow is present, this arrow is absent, and then they run,
yeah,
hey,
it is kind of missing that, yeah.
yeah, that's all. But then an interesting, I don't know, let me get that question.
Yeah. So I understand about the causality variation of autoencoder report, but I don't know how they identify the potential biomarkers of brain disorders just by the construction error.
Yeah, so I think they're considering I think they're considering this a form of a biomarker because they're seeing kind of like these group differences in these particular brain areas, which they kind of identified with existing literature as being kind of biomarkers for these particular disorders. So I think they're also considering
Methodology, right? In terms of identifying the biomarkers.
what was the question?
What is their approach? What is the methodology? How they use this framework to identify the potential biomarkers of Alzheimer or ASD? How do they use this framework for identifying biomarkers?
Yeah, I think the main thing that they're really doing is kind of just looking at group differences, really, between these causal representations. So from what I understand, they they compute the causal representation of all the data, and then they probably take an average of some kind, and then they look at the group differences from and then they consider that some kind of a biomarker.
So I have a question from TJ. Did they make any connotations on the EMCI and PMCI difference from the ADNI group? There have been past studies to debunk these delineations, which is why ADNI 2 to ADNI 3 dropped the labels. This was pre-called. Do you know, have you seen anything? Okay, maybe TJ, you can, if you have your microphone, yeah.
Yes. Test 1, 2. Can you guys hear me? Test, test, test. Maybe I'm not. Okay. Yeah. So really, I saw papers back in like 2018, 2019 that were trying to they debunked the delineation between early and late MCI, not PMCI. I apologize. But they basically looked very similar when compared to the general MCI as well. And so that's why the ADNI 2 to ADNI 3, they dropped the labels. And I think this paper is from like 2023, if I'm wrong. And so I was just wondering if the authors made any connotation to these differences, because I know that really it's hard to discern between the two since there's such limited amount of data.
Yeah, I'm really not sure about that, to be honest. I don't think I noticed anything there.
Okay.
Yeah.
Okay. Yeah. I mean, it's great access to this data, and I really love having such large amounts of Alzheimer's data since it's so hard to capture. But I just know there's so much the dissonance with this data set.
Mm.
That was my final question. Why did they mention jokes in the sense of those others?
I'm trying to remember if they did. Uh, yeah, I'm not really sure off the top of my head. I can look really quick, but yeah, I'm sure. Oh,
You mean the paper?
yes.
While you're searching, you can entertain people with relate to thought.
No, yeah, go ahead. I'm really not sure. I'm browsing.
Yeah, so the interesting part is the the adjacency matrix of causal structure is kind of the way we think about it as a mechanism. And imagine just any mechanism that you've seen, gears connected by cogs and stuff like that. So the same mechanism, you can rotate with different speed and get different measurements, different signals, like they will look different, but the mechanism is the same. So you can run it fast, you can run it slow, you can run it in a jerking kind of fashion, stop, run, stop, run. You can generate different types of behavior from the same mechanism. But say for and this different type of behavior from statistical point of view will look like distribution shift, because when you're running fast versus you're running slow, your distributions of data are different. So this is when you're training a deep learning model on fast data from the same mechanism. But then you're training a deep learning model, not training, applying to predict from the same mechanism but from slow data, it will be wrong because the distribution have changed. But if you're using the mechanism itself, the causal structure as your feature, it's all the same. It's stable. It should be predictive, no matter like it's much less prone to distribution shift because we don't think our brain mechanisms change that much, right? From day to day, from people to people. Mechanism is the same. The way this mechanism works is different. So in that regard, the stable of theirs with any five sites, what is it? The different five sites is interesting because they are using adjacency matrix for prediction, and yet something like you said, NYU, like there is a large variation in predictive power. It's pretty much, I mean, look at the things that are stable versus the things that are changing. So what I would have expected is that correlation matrices, the first, the PC naming is so bad because there is another algorithm that is called PC, just in the line, the causal discovery algorithm. In any case, which of those methods is stable across the sites? I wonder. They all should, because causal structure should be similar across the sites. But that's just an interesting observation. It's a hypothesis. It's not that it's like set in stone causal mechanisms, but I don't see a logical reason for it to be otherwise. But interestingly, that even correlation is quite stable across the sites. It stays at 66 accuracy. Although, yeah, the one change, or if one changes a lot, but accuracy means nothing. Sites are misbalanced. Like it's a data balance. So.
Any other questions?
And this is how they would the signal prediction. Because some books and stuff, but then it's like the prediction. It's stuff to start.
Could you repeat the question? Yeah, I'm
Look at how they do some construction.
the signal reconstruction.
Yes, the original. But they're doing one time point at a time. Decoder. And like encoder gets also just one time point at a time. All vector of all components activations. Next vector of all components. What they're sampling looks like is the means. Okay, here, if you're going for DMAP talk, that's next door. Yeah, we're almost done. No questions? Do you want to ask something, Joanne? You were looking for stuff in the paper.
No, yeah, I'm not sure about their choice of the data set. They don't really mention too much.
You mentioned schizophrenia. I did notice that. They did also mention as a small sample size.
Yeah, I'm not sure, Jay, to really answer your question, but you're kind of vague on why they chose these data sets a little bit. But yeah, anything else?
Yes, thank you.
Somebody online had a question. There we go. I don't know why they're coming out of a different speaker.
No, it's a,
Oh. That's why. Okay.
we're fine. Yeah. Okay, thanks everyone online joining, and thanks for people who managed to watch here at this point. We're putting, yeah, it's on YouTube. So, thanks, Joanne, for presenting. Very interesting.